Welcome back to the show. It's been a while since I made a video. The last one I think I made was on cues a while back. But today we're going to be talking about tries in terms of what they are, and we're going to create tries two different ways in Python. And my name is Nathan Patnam. So what exactly is a trie? A trie is a data structure for storing items, usually strings, and we store them based off of the prefixes that these items share in common. And so we'll talk about exactly what this means in a second. So imagine if we wanted to store the words wait, waiter, shop, and shopper. We see from a high level that wait and waiter share the same four letters or the same prefix of WAIT, and shop and shopper also share the same prefix of SHOP. So you see a relationship between the first two items, and you see a relationship between the last two items based off their prefixes that are in common. So now let's talk about how we can maybe represent these four words inside of a trie structure, and then we'll talk about how exactly inserting into a trie works, and then we'll code it up. So if we talk about a list, this is kind of how Python or really any language stores strings in a list format. Each row represents a whole string, so wait, waiter, shop, and shopper, and each bubble represents the individual character being W-A-I-T for wait, W-A-I-T-E-R for waiter, and so on and so forth. But a trie, kind of like the name sounds, is a tree-like structure, where at the very top you have this thing called a root, and each node or each bubble has children, which it knows it connects to. So imagine we look at this trie, we want to check to see if the word wait is in this trie. So what we do is we start from the top, the root, and we check to see if the root has W as any of its children. And we see that it does have a W as one of its children. So then we go down to the W. We kind of move our pointer down from the root down to this W. And then we ask ourselves the question, does this W have an A as one of its children because the second letter of wait is A? And we see that that's true. And then we follow that same pattern for I and T. Once we get to the bottom of the string, we need to denote in our trie some way that this path that we've gone through, W-A-I-T, is in fact a word. And one way that we do that is by adding a symbol, and in our case here, we're adding a star, just like the first symbol in our trie. And so we can see that waiter is a word because we can take W-A-I-T-E-R and we see that there's a star there. But imagine we wanted to find the word maybe waiting. So we start with this W, we go down to A in waiting, the I, and the T. The fifth letter in waiting is an I, and we see that I is not, this T doesn't have an I as a child, and so we know that waiting is not a word in our trie. Now let's go over real quick time complexity. So the time complexity to check, and in our example here, we're going to check to see if the word shopper is in either data structure. To check to see if the word shopper is in our list, what we need to do is we need to go through each word, which is order and time, because we have to iterate through every word in our list. And then for each word, we have to check to see if that word we're looking at is the same word that we're trying to find. So we look to see if wait is shopper, which is not, waiter is shopper, which is not, shop is shopper, which is not, and we see the last word shopper is shopper. But one thing that we have to keep in mind is that in Python, or in any language really, when you compare two strings, that's an order M operation where M is the length of the string you're comparing because you have to compare each character one by one. So that's why to find or check to see if a word is inside of a list, that's actually O of nm time, where n is the number of words in the list and m is the length of the word you're looking for. Because worst case scenario, your list doesn't contain the word you're looking for, so you have to go through every word. And each time you're doing that, you have to compare each word that you're looking at. In a trie, you have better time complexity because you don't have to do all these unnecessary computations. In a trie, to check to see if a word is in there or not, is order O of M, where M is the length of the word you're looking for. Because what you do is you start from the root, you check to see if the first letter that you're looking for is a child of the root. So maybe we're looking for a shopper, and we see that S is there. And then you go down to H, then O, then P, then P, then E, then R. And so at every given time, you're only really going the number of letters in the string you're looking for. And at any time, if say you're looking for shopping, we get to this P right here and we see that I is not there, then we stop because shopping is not a word in our trie. Also note that adding a word in our trie only takes O of M time, where M is the length of the word to be added, because all you have to do is say we're adding the word shopping, we would go down to the S, the H, the O, the P, and then here's where we would add like an I, an N, a G, and a star symbol. So now let's go over a quick example about how we would build a trie. So when we create a trie at the very beginning, we would have a root that's already created for you, and I denote as a star. And imagine we want to add the word wait. So what we do is we start from our root and we check to see if W is a child of the root, and we see that it's not, so we add it. And then we check to see if A is and so then after we add the W, we move our pointer down from the root to this letter that we just created, and we check to see if A is a child of W, and it's not, so we add it. And then we do that pattern for both I and T, and once we get to the very end, we want to denote that this path that we've just built is a word, so we add a star. Now imagine we want to add the word waiter. So similarly, we'll start from the root, but here we see that W has already been added, so we don't need to add it again. So we move our cursor down. And then we do that same thing with A, the I, and the T. The E, because we don't have an E here yet, is a letter that we have to add. We add the R, and then we add the star to represent that this path is a word. Similarly for shop, we go from the very beginning, starting from the root. We add our S because S is not a child of the root. We add the H, the O, the P, and the star. And then for the last word shopper, we go down the S because the S is already there from the root. We start from the root and we go down to the S, the H, the O, the P, and then we add the P, the E, the R, and the star. And so do you notice how the word W-A-I-T is only printed once, even though two words use wait in its word? And that's how the prefix here, we're only storing the common prefix for both words. Same thing with shop. And so that's why if you have a lot of words that share prefixes, it's much more efficient to store it this way because we only have to store the different letters as opposed to every letter like we had to do, let's say, in a list. So let's talk about two different ways that we can implement a trie. One way of implementing it is where we have a trie node and it has a letter member variable, which is a character. It has a Boolean telling you if that node is the end of a word or not. And it also knows its children. In the trie class, you will have a root, which we would instantiate to be an empty trie node. And then you would have your add word and does word exist methods. And the add word doesn't return anything because you're just adding it to your trie. And the does word exist will just tell you if the word is in our trie or not. And that usually is a Boolean. In the implementation two, what we do is we don't really have a trie node. We just have a general trie class. And our root is just a dictionary that stores the letters that it has as children, and then it stores the second letter that it maps to. So in our case here, if we started with the root, we might have a W, which maps to a W for wait, and then that W here would map to an A, and so on and so forth. And then we would have the same add word and does word exist Boolean. So now let's talk about how we can code it up. So I'm going to move over to REPL real quick. And so here we have our example up here where basically I want to be able to create a trie. And then I want to be able to have a list of words where I go through each word and add it to my trie. And then at the very end, here are a couple of unit tests I have where I check to see if the words exist. Wait, since we're adding it from words would exist. The empty string is the prefix for pretty much any word, so that's always true. W-A-I-T-E has not been added. Even though we have this prefix of W-A-I-T-E, that's not a word, so it doesn't really exist, and we would return false. Shop is the word that we add, and does word exist, S-H-O-P-P. That one is not a word that we added, so we would return false. So let's build out our trie. So we would create our class called class trie. And here we would, in our constructor, we wouldn't really take in any variables when we instantiate it, but here's where we create our root. And our root from the very beginning is just a dictionary where we have a star character, which maps to a star character. And this will help when we pass in the empty string to make sure that it will return true when we look it up in does word exist. So now let's create our method called add word. And add word takes in a word. And what we do here is we have a pointer that will start at the root that we kind of have here. And as we work our way down, when we're adding the letters, that's kind of how we build it out. So if we go to our first case here, where we start with the root, we add the W, the A, the I, and the T. So what we'll do here is we'll have our current node, which will point at the very beginning to our root. And what we'll do now is we'll iterate through each letter in the word that we want to add. And what we have to do here, we have to check to see if the letter that we've added was there or not previously. So in wait, we can see that W, A, I, and T are all added for the first time. But when I go to waiter, we see that W, A, I, and T were already added from when we added wait before. So we don't really need to add those same nodes again. And so here's where we can make a check to see if the letter is not in current node. Then what we should do is we should create at the letter a new dictionary that will store the children of it. So for example, when I want to add W and weight, what I would do is I'll start from the root, and because I wouldn't see a W yet, I would add the W and would have no children attached to it. So for the example here, I would add W, and when I try to add the A to it, what I would do is I would add A, and it has no children, and that's what we use the dictionary for. So that's why we instantiate an empty dictionary right here. And then once we add that dictionary, this is where we can actually assign that character as one of its children. So we can say that the cur node at the letter. Oh, and so once we create the empty dictionary, what we can do is we can now move our pointer down. So we can say something like cur node equals cur node of the letter. Because what we did here is we added the node, and we said that when we added the node, it has no children. And now we need to move our pointer down to the next word. And after we've added our word, what we need to do is we need to take the current node, and we need to say that we need to add a star character, meaning that this is an end of a word. And so that's all we need to do for adding a word. To check to see if a word exists or not, we'll do something similar where we have a current node which points to our root, and we'll iterate through each letter and word. And then we'll check to see if the letter that we're looking for is not in the current node's children. And if it's not in there, then we return false. And let me see. So we said for letter and word, and then we say if letter is not in the current node, we return false. And like before, if we do see the letter as a child, then we move our pointer down to that next thing. So in our case here, say for example, we're looking for wait, let's say we're looking up the word waiting. We see that there's a W, so we move our pointer down from the root to the W. We see there's an I, so we move our pointer down to the or we see an A, so we move our down to the A. We see the I, we see the T, we move to the E, and we move to the R. So that's how we know the word is there. But maybe we're looking for the word waits. We get to this T part, and here we see that S is not a child of T, and so that's why we return false. So then we move our pointer down to be to the letter. And the last thing that we need to do is we need to check to see if there's a star at the end of the path, which means that the path that we've gone through, so W-A-I-T, this is actually the end of the word. Because the star wasn't there, then W-A-I-T, that wouldn't really mean we're at the end of the word. That would just be a path. So here we would check to see if that is in current node or not. And so if we run our code, we get that wait does exist, which we expected. The empty string does exist. WAITE does not exist. Shop does exist, and SHO with 3Ps does not exist. So now let's go over another way that we can implement this try. And this way is how we can implement it using a try node. So we would have a class called try node. And when we create a try node, all we need the root to be is when we create a try node, we need to have a couple of properties with it. We need to know the letter being passed in, so the try node knows what letter it is. It knows what its children are. And it also knows if itself is if it's an end of a word or not. So in this case here, like when we had the try class in the previous example, we had to put a star here telling us that this path that we got to was a word. But in this case here, what we'll do is we won't have that anymore. We'll just have this T have a property inside of itself that knows whether it's the end of a word or not. So we'll make something called is end of word, and we'll set this be equal to false. So now we'll have a class called try. And here we will do something similar where we have a root, and this will just be a try node where we can pass in a star symbol. We'll have the same two methods for our interface that people can interact with, so we don't have to change any of the code below. We'll have add word, which takes in a word. And what we'll do is kind of like before, we have a pointer that starts at the root, and we iterate through each character or each letter in word. And if the letter is not in the cur node.children, So if we haven't seen this letter before, we need to add it. So we'll say cur_node.children at the given letter equals to a new trie node with the given letter. So that's how we can create these children about it. And then after we create in the new letter, then we can move our pointer down to become the cur_node.children of the letter. And just like what we did before, at the very end, instead of adding a star symbol, we'll just take the current node, because if we added the word waiter to it, our current node at the very end would point to this R. We can take this property as end of word, and here we can just set it to be true, which marks that this node is actually, in fact, an end of a word. So now let's add our method, does word exist, which takes in a word that we're trying to look up. And similarly, like the example above, we'll have a node that points to our root, and then we'll iterate through each letter in our word. And here we'll check to see if the letter is not in cur_node.children, then we return false. One thing that we have to do a checkup here is we'll have to check to see if the word that's being passed is an empty string or not. So if the word is equal to the empty string, then we can return true, since the empty string is technically the prefix for any other word. And so in this bottom case on line 47, if we don't see the letter, so in our case here, imagine we're looking for the word waits, W-A-I-T-S. We go to the W, we see there's a W, we see there's an A, we see there's an I, we see there's a T, but we don't see there's an S, we return false. Like before, what we need to do is we need to move our pointer down if we do see the letter as a child. So cur_node will be equal to the cur_node.children of the letter. So we can move our pointer down. And at the very end, all we need to do is check to see is if the node that we reach to at the very end is an end of the word or not. And that's what we can return back. And so if we run our code, we get true, true for the first two. Wait is a word in our prefix. The empty string is a word in our trie. WAITE is not a word in our trie. Shop is a word in our trie. And shop with 3 P's is not a word in our trie. Here are two examples of making it. So some questions that a trie can help you with is, let's say you're given a list of words and you're asked or tasked with finding if a word is in that list of words. Instead of using a list where you have that O of n times m time complexity, maybe making a trie and doing a traversal may be faster, especially when you get really big lists. Another question I've seen is, given a list of words, find the longest prefix that is shared by the most amount of words. And so what we could do is you can just kind of traverse down your trie. Once you hit a prefix, you can kind of move on and see how many words can be made with a certain prefix by finding the star symbol. Thanks again for watching today. All the code will be in the description of below. A link will be posted to it. Let me know if you have any questions or comments, and I look forward to seeing you in